Hello, my name is Sahil Kirangi, and this is Physics Lab 3 on black hole and orbits. So as an introduction, in this lab, I created two main computational models in GlowScript. So one analyzed the motion of a star, including the net force on the star overall to estimate the mass of the black hole that's affecting the star. And in the second computational model, I simulated a spaceship being affected by the gravity of a planet and the planet's moon. So by looking at all the gravitational forces and using Newton's second law, I simulated the orbit of the spaceship in the planet-moon system. So the key concepts used, we use the gravitational force. This force allows for the estimation of the mass of the black hole by using the net force and looking at the distance between objects. Also, Newton's second law, delta P over delta V, this determines the overall rate of change of the momentum and lets you determine the gravitational force that acts on the star. And velocity and momentum, they just describe the velocity describes the position over time, position change over time, and the momentum describes how the motion of the star changes. This is just what we used in both models. And our FNet equation, the main one that we used was FNet parallel plus the FNet perpendicular. These are our initial conditions for the black hole, so for the first computational model. And then these are the calculations that I used for the black hole computational model. So this is what I did for the vector for delta V, delta P, and I calculated dp dt as delta P over delta T, and FNet is obviously dp dt. This is the calculation for that. And then the code for the arrows. And notice over here, this is the actual mass of the black hole that we did. So that would be the magnitude of FNet multiplied by the magnitude of the position of the star squared. And this would be divided by the gravitational constant multiplied by the mass of the star. So this was about around 7.2 times 10 to the power of 43. And this is just our code that I used for the arrows. So these are the results for the for the orbital system on part 1. And this describes the arrows. For our computational model part 2, these are our initial conditions once again. Now for the second model, the calculation loop. This is the calculation loop. The top image over here on the right is the calculation loop for the net force of the moon. So this depicts the planet to the moon and then the ship to the moon. And it adds up the force of the ship on moon and the force on planet on moon to calculate FNet on moon. Similarly, this works the same way for the spaceship. Calculate the force of the moon on ship plus F planet on ship to get the FNet on ship. And then these are our initial conditions. So this is the initial conditions I set for X and Y. Notice that it cannot move faster than the speed of light. And this is how the model looked like. So possible sources of error I had is the fact that the floating point and arithmetic error. So the computational model automatically simplifies long decimals, and implementing them would simplify that. So doing so ends up reducing the overall accuracy of the model. This changes certain vector placements and whatnot. So it doesn't give completely everything completely. And in real-time systems, so in this specific experiment, this doesn't necessarily have as much of an effect, but if we looked at this experiment through like a realistic lens, through actually like an actual outer space standpoint, the systems being studied here are not just in like a void space or like just a planetary void. They would also experience gravitational effects and forces from other neighboring planetary systems, and we'd have to take that into account into the equations. What does it mean? So how are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel perpendicular components? So they just differ in the actual calculation. To calculate the actual rate of momentum, you just need the system's change in velocity, while on the other hand, we can't directly calculate the force, so we can just infer it using our calculated momentum. And finally, our what if question. Well, this imaginary system has a black hole. What if it has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? So in this case, we would need to incorporate the gravitational forces acting on every object, and we have to look at every single one. So in this case, all the forces between black hole, star, planet, and moon. That's how we would get our FNet. And further, because the force depends on both mass and distance, the gravitational force, in fact, some interactions would dominate more, like the black hole and star, while smaller interactions would have less of an effect. Thank you.